Right, so next we have the final lecture by Harald.
The final lecture within the context of this school. I hope. So, well, recall. All right. Where were we? We were working with a group of Lie type G, a linear algebraic group, and then G is its Lie algebra, and we assume that G is simple for simplicity. That's generally the case if G, big G, is itself almost simple, saving tiny characteristic. Now, what do we have? We have that when your Lie algebra is simple, so what we did at the end of yesterday was that if you have two subspaces with dimension intermediate between the dimension of the space and 0, then there exists a G in G such that if you conjugate, that is, if you act with add G, so add G V prime, which is the same thing as G V prime G inverse, this will not be contained in V. So there exists a G such that the conjugate of V prime by G is not contained in V. And so in that case, V plus GV prime G inverse has higher dimension than V. So yesterday we saw how we could bound the number of points on a set A that grows slowly that are contained in a maximal torus. Now I will show you how the exact same strategy can be used to bound the number of such points on an arbitrary one-dimensional variety. So let V be one-dimensional. We choose first G1 such that the conjugate here is not contained in V, I mean V prime here. And then we choose G2 such that, so we could define then V2 to be the sum of these two, but let me just write, we choose G2 such that the conjugate here is not contained in the sum of these two. And we go on and on. We make the space bigger and bigger at each step. So G3 such that G3 V prime G3 inverse is not contained in the sum of all of these. So what do we have? We are increasing the dimension by 1 at each step. V prime are one-dimensional, and so on. And then we obtain what? We obtain then that phi from V, here are R copies, to G. Well, the map here given by this vector gets sent to V1 times a conjugate here, and so on. This has non-singular derivative at the origin. Why? Simply because what we have just shown is that the image of the derivative at the origin has full dimension, has dimension G, or has dimension R, same thing. If you have a linear map from an R-dimensional space to an R-dimensional space whose image has R dimensions, well, then you know that the map is non-singular. But then, again, how do you tell whether a map is singular at a given point? Well, you just take the determinant of its derivative. So being non-singular at a point is a generic condition. I think it fails to be the case on a subvariety of the variety you are working on, we have just shown that there's at least one point, at least the identity, not lying on that subvariety. Hence, that subvariety is of positive codimension if V is irreducible. So, if V is irreducible, so is V, and hence, by showing that the subvariety W where d phi is singular is not V. It's not that because it does not contain the identity. That's what we have just shown. We have shown that the codimension of W is positive. In other words, this is the same as saying that phi has non-singular derivative at x generic for our specific choice of G1 up to GR. But, so G is simple, and now what is really relevant is that G is irreducible as a variety as well. I should state that assumption. By exactly the same argument, you get that because there are G1 up to GR for which, or G1 up to GR minus 1, for which this is the case, we have that the variety of G's for which that is the case is a proper subvariety of positive codimension of G, or G to the R minus 1. So this has to be true for G1 to GR minus 1 generic. And that's all we needed. Then we run exactly the same argument as yesterday. No? It's a counting argument. Because you have that the map has non-singular derivative at x generic for G1 up to GR minus 1 generic. So first of all, you can find such G1 GR minus 1 in A to the O of 1 by escape. And then by counting, so almost injectivity, you get the statement we wanted. So let this be an algebraic group. Irreducible. And the algebra is simple, slightly stronger than asking for just for G to be simple. A in GK, A generating GK, V G of dimension 1. And you can assume that V is irreducible without loss of generality. You just decompose it into irreducible subvarieties. And you obtain, by the same argument from yesterday, using this fact we have just checked, that this intersection is at most A union A inverse union the identity to the K. And now it's to which power? Exactly, 1 over R, 1 over the dimension of G. No? Now, this is actually just a special case of what we can prove. As I said at the beginning, we can actually prove that for V general, V of general dimension, it's just that instead of 1, we will have the dimension of V. Let me prove that for you in the case that we actually need, and this should give you the general idea. Yes? I already said that, yes. So that's why I'm assuming the little g is simple.
Okay. I see.
Yes, I mean, in general, it's not actually a problem because you don't have to work over the Lie algebra. There are other approaches, but I find that this approach is the most intuitive, at least for me. So to repeat, when the characteristic is small, the fact that big G is simple does not necessarily imply the little g is simple. Now, what about higher dimension? So The example that will work out is example we need. So let Vt be the subvariety of SL2 given by, well, of course the determinant has to be 1, that's why you are in SL2, but also the trace of G is equal to a certain constant T. Now, why do we care about such a subvariety? It's because the conjugacy class of an element is always contained in V of trace of G. Now, the trace is invariant under conjugation. That's what this means. Now, let me state the proposition and I will sketch you the proof. So, it's just the same as before. A in SL2K and for every T in K, distinct from plus minus 2, trace 2 and minus 2 is sort of evil because, you know, that includes the case of 2 eigenvalues equal to 1, you have unipotent elements. This is the same as asking for things to be regular semi-simple. So for any such T, you have the intersection with VTK is at most, or well, what you would expect here, where the constant K and the implied constant here, they are both absolute. We are in SL2, so it's a constant. So let us sketch the proof. So phi from Vt cross Vt to SL2, I'm going to define it quite cheaply as y1, y2 gets mapped to y1, y2 inverse. Now, is this map injective? It doesn't have a hope of being injective because the dimension of the space here is the sum of the dimensions of Vt and Vt, so the dimension is 2 plus 2 equals 4, whereas the dimension of SL2 is, of course, 3. However, what we can try to do, well, we no longer have that the pre-images are of constant size, they are not zero-dimensional, they will in general be one-dimensional. But we can control the size precisely because we have already given bounds for the intersections of sets with one-dimensional varieties. So, for H in SL2K, we are going to examine the size of a pre-image. So this is like that. Well, you know, that's determined by the first coefficient for H fixed. So we really have to look just at W. So we define, so ZTH we defined as, so we have to control the size of these. So W such that in GL2 it's understood such that the trace of W is T and the trace of H minus 1W is also T. So and this has dimension 1, sure enough, provided of course that H is not plus minus identity. So as I said before, you know, we can apply this result with V equal to ZTH, right? But that's all we needed, because then what do we obtain? We obtain then that we can so let me see. So we can compare. Yeah, on the one hand, here, what are we going to have on the size of the domain? We're going to have A VTK, and here, just as yesterday, we have to subtract 2 because we have to subtract the pairs, the weight 2s that would give us a quotient equal to plus minus identity. And this here is at most what? AA inverse. Why? Well, this is where the elements y1, y2 inverse live, times, well, this bound over here, right? No? But this is, of course, you know, you want 4/3, and then you take square roots, and you have exactly what you wanted. You have this bound here. Now, this argument works in general. the idea works in general. And you can find this as a worked out problem or a problem with some hints in the notes for V of arbitrary dimension. Of course, we got slightly lucky here in the sense that we took this very simple map. So what kind of map do we take? Well, exactly the same map, the same sort of map that we took before. So consider maps like this, V, V, well, so it's V times V. This takes V1, V2, not just to the product or the quotient, but, you conjugate by something. And again, by the simplicity, you are always going to have that you are going to be able to pass to a lower dimension, just like here. You reduce the problem to the problem of proving this sort of bound for V of lower dimension. In this case, dimension 1. Very well. Now that we have a bound like that, so I said ages ago on Saturday that upper bounds are very nice, but what is really beautiful is lower bounds. And there's one way we can get lower bounds from upper bounds, namely by the orbit stabilizer theorem for sets. So you apply the orbit stabilizer theorem. We even considered it under the action by conjugation, remember? And we obtain what is called corollary 28 in the notes. So we obtain that for A in SL2K, A generating SL2K, if A cubed is not much larger than A, obtain that A minus 1, A inverse C of G is at most A to the 1/3. So why do we obtain this? Because we were getting, I just remind you, so here you get, by the orbit stabilizer theorem, you get that is at least A, and here you have A cubed intersection the conjugacy class. But here, this is precisely what we have just bounded. No, this is A cubed intersection VTK. So you obtain what we wanted. So this is the one-line proof. Any disagreements? Please verbalize them in public. Some people at the back. Very well. All right. So once you have that, you're in very good shape for G regular semi-simple. So meaning, this is just a fancy way of saying it has two distinct eigenvalues. So it's not just two eigenvalues equal to 1 or minus 1. So now that we have that, it's wonderful because we have really a full deck of cards, so to speak. We have lots of elements of a special form. And well, once I had that back in 2005, I sort of knew I was going to win. I was going to get the result I wanted. Now, there are many ways to finish it, and I will give you a rather modern way that works almost in this way for SLN. There's just one particular spot in which I will be using the fact I'm in SL2, and it's not essential. So, here. The proposition I want to prove, the main result of this course, is the following. And either A cubed is big. And remember that for this it's enough to show that A to 100 is big. That implies this. Or A is already very big. And if there is time, I will get a further consequence from this. So when you have that A is this big, this means that A cubed is already the entire group. Back in the day, in 2005, I had a to the 10 or what have you. And I did it with my bare hands, but there's a rather elegant way to get this implication. And we will do it at the end if there is time, or at least I will sketch it for you. So how do you prove this? So first of all, as usual, by escape from subvarieties, there exists a G in A to the O of 1 that is regular semi-simple. And this just means that the trace is not plus minus 2. And this is so by escape, because having trace plus minus 2 is a special condition. It's an equation. Now, our good friend the pivot. So we call psi a pivot if this is injective. Well, let me be slightly careful. I'm going to take quotients by plus minus 1. It's a technical reason. It will become clear why later. And if it doesn't matter. But I will make it clear. So I want this to be, so this is a map from A, C, G, but I take quotients by plus minus the identity to G of K plus minus identity. So we have two cases as usual. So case A is when you have a pivot in your set and you are very happy. The second case is when you don't have a pivot anywhere, when pivots don't exist, and then A has to be big, and you are done pretty quickly, in fact more easily than last time, if you just want this conclusion. And the third case is when pivots and non-pivots exist, and then you use precisely the point of passage, the moment of passage from non-pivotness to pivotness to win. Non-pivots are reachable, pivots are useful. Since I generate G of K, there is a single step from some non-pivot to some pivot, and you are done. All right, so case A is when there exists a pivot chi in A. Then what do you do? So by corollary 28, there are plenty of elements in C of G, in that maximal torus. Let me just O of delta. Elements of AA inverse in CJ. So, what do you do? By the injectivity of phi G, I have that the image is as large as the domain, right? Or since I'm taking quotients by plus minus 1, I could have a shrinkage factor of 1/4. So let me just take 1/4 A minus 1 A CG, and this, as I said, is large. So you have that this is at least A to the 4/3 minus O of delta. Very well. But phi xi, this is in A, this is A inverse A, and xi is also in A by assumption. So this is going to be contained in A to the 5th. We have proven this. And, well, we can assume that O of delta is bigger than a constant, otherwise the conclusion is trivial. And delta smaller than a constant. This would contradict, well, this actually implies, A cubed. A to the 1 plus delta. No, simply because even if we had proven it for A to a million, this would imply that A cubed is also big. You just divide this by, well, 5 in this case. So you're fine. Very well. So case B. No pivots in GK. So for every, this means that for every chi there is a collision. For every chi there exists A1, A2 in A, T1, T2 in T of K, and they are distinct, even modulo plus minus 1. And they collide. Their images are the same. So this is, of course, phi xi of A1, T1. And that's going to be equal to phi xi of A2, T2. So plus minus that. And so just taking quotients, we obtain that, yes, we obtain that xi T1, T2, T1 inverse, psi inverse, plus minus A2 minus 1, A1. In other words, for every xi, A inverse A has a non-trivial intersection with xi T xi inverse. So this is not contained in plus minus identity. Very well. By the way, brief note, case B never occurs when K is infinite. So much the better. K equals R, K equals C. If you want exactly the exact same statements are easier, not harder. But let us continue. So you choose any G prime here, not equal to plus minus 1. So G prime, and here, it's here, not elsewhere, we use the fact that we are in SL2. It's not a tragedy if we are in SLN, we have to make the argument a bit more involved. But so you have that since G prime is in a maximal torus, and G prime is not plus minus E, G prime itself is regular semisimple. I mean, if you have an element of a torus, a diagonal element in SL2, and so it's R, R minus 1, and R is not plus minus 1, then R is different from R minus 1. So this warning is just the fact that in SL3, you can have things such as RRS, right? Where they are not, this is not regular semisimple, yet it's not the identity. You just find R and S such that R squared decimals. This is just a little warning. So here we are not in SL3, so G prime is regular semisimple. And moreover, you have that CG prime, so the diagonal, you are in the diagonal matrices, you have a diagonal matrix that is not plus minus E. Its centralizer is again the group of diagonal matrices. So G prime equals xi tk xi inverse. So this is good because you have G prime is an element we like. It's a G prime is an A inverse A, and you're looking at the centralizer, and we can apply again corollary 28. So, by corollary 28, we obtain that A inverse A this is at least A to the 1/3 minus of delta. Now, there are, well, at least half of all maximal tori in the group are of the form xi t xi inverse. Why only half? Because you could also have the conjugates by something in the extension. But it's easy to show, basic algebra, that there are at least 1/2 g of k t of k, g of k t of k being the total number of maximal tori. So at least as many maximal tori. I mean, you can prove this directly as well. It's really triviality. Are of the form, yeah, because two conjugates are the same only if their quotient is plus minus identity. So of the form xi t xi inverse And you also, so you have lots of maximal tori, you have lots of elements of A inverse A in each maximal torus, and you also have that an element that is not plus minus E can lie in at most one maximal torus. Does anybody disagree? No? I mean, that's clear. You have a diagonal element, and if you change the basis, it's no longer going to be diagonal. So, unless it's plus minus identity. So you have, well, you just have to multiply this and that then. So A inverse A, so you count the number of maximal tori, you count the number of elements that are not plus minus identity in each of them. So let me write a little constant here. So here you have C, A 1/3 minus of delta minus 2. No, and this is at least what? Well, it's at least K squared times A to the 1/3 minus O of delta. And hence, either A inverse A is much larger than A, say 1 plus 2 delta, and this implies, of course, that A cubed is, again, by Ruja. I should say Ruja here as well. Or A is huge. No. The only way that this thing is not going to be bigger than A to the 1 plus 2 delta is if A is already of size almost K cubed, that is of size almost SL2, which is what we wanted. That was the other conclusion. So we go on to KC. So there are pivots and non-pivots in GK. Hence, since A generates, G, it's always SL2. I hope I said that before. Well, it's clear right now that G is SL2, I hope. Since A generates G of K, we have that. This means that there exists a non-pivot and A in A such that, well, A union A inverse, if you wish, such that A psi G is a pivot. Now, what do we do? Since psi is not a pivot, we have precisely this property, right? So you have loads of elements. You have at least one element, and hence you have this thing here. So 2 stars also holds. That's good. But we also have that since A psi is a pivot, the map given by it is injective. Quotienting by plus minus I. So phi A psi A, and here I'm going to create psi minus 1, A, so that this will lie in T. No? Psi T psi inverse psi. So this lies in T. This will be at least 1/4 A, the size of that, which is not changed by conjugation, obviously. So it's AK psi T, psi inverse. And this is at least, well, yeah, a to the 4/3 minus O of delta. Very well. But we also had that this is contained where? This is contained where? Well, remember, this is A times xi, and all of this here, then xi inverse. So the xi's cancel out, and you have that it is contained then in A to the k plus 3. The xi's die. All right, but then we obtain A to the k plus 3, A to the 1 plus delta, and no, this 1/4, A to the 4/3, and this implies A cubed. Yeah, so in the notes there's an nasty typo. It's an inequality in the statement is in the wrong direction. You should be careful with that. Not in theorem 34, but in the proposition. So A to the 3rd, I will correct that, is greater than 1 plus delta, if you wish here. 4 delta small enough. By Rusha again. And that's it. No? So we have proven the main theorem of the course. We have proven that there is growth in SL2. No? We have proven this statement here. So now let me just sketch for you, and I do think we have enough time, what I said in the note, that when A is very big, A cubed is all of SL2K. Back in the day, I mean, it's something, when A is really big, you can take quotients by a Borel, you end up working in the field, it's not very hard. However, I think it's even nicer if you give a proof that helps us review some other concepts. So the proof I'm going to sketch now of this implication, I mean, the basic idea is much older, but the application here is due to Gowers and Nikolov-Piver. So remember that you have the adjacency operator. So add linear operator on the functions from G to C. And how does it act? Not add, excuse me, A. And AF is going to be, of course, another function from G to C, and its value at G is the average of the values at the neighbors. And this is a symmetric operator, so it has a full real spectrum. Its silly eigenvalue is 1. Constant functions are taken to themselves. You know, this is a function that replaces your wealth by the average of the wealth of your neighbors. So if everything is constant to begin with, then that's unchanged. So you have the constant functions are eigenvectors with eigenvalue 1. And then you ask yourself, what is the spectral gap? And in general, as I said at the beginning, that's a difficult problem, and people have proven things about that using precisely this proposition. But when A is really big, that's actually fairly easy due to an old idea that also gets used in the difficult case. So it's one of the oldest tricks in the book is that you can, the trace of an operator to the, say, R, can be expressed in two ways. On the one hand, it's 1 over A to the R times the number of returns to the identity, right? Simply because when you take a trace, well, you are adding all the entries in the diagonal, and if you start with a matrix A, that is basically a matrix with zeros and ones, a matrix that gives you which points are neighbors in the graph, the way you are going to get something in the diagonal, so every entry in the diagonal counts how many ways are there to get from a point to itself in R steps. So this is very well. And on the other hand, you have that this is also the sum of the eigenvalues to the R. Now we're going to do something. This is the general trick, but generally you try to make R quite large or R middle-sized, but we are just going to work with R equals 2. Here you have lambda I squared equals 1a squared. And what is the number of returns to the identity? There's basically only one way to return the identity in 2 steps. That's it. So you do it for each of the G points, and well, there's only, depending on the edge you take, it's A. No? So you do it either this way or this way. Very well. At the same time, you have, and I think I mentioned this briefly the other time, that all eigenvalues except for lambda 0 have high multiplicity. Why? So the multiplicity is how many times lambda 1 gets repeated, how many of the supposedly lower eigenvalues are equal to it. Why? It's because the space of eigenfunctions of eigenvalue lambda 1 is invariant under G acting from the right. So it is a complex representation. So it's a complex vector space in which G acts. And because this is not a constant function, it's a non-trivial. Now, there's a theorem by Frobenius, which in the case of SL2 is actually fairly simple, but it's a beautiful general theorem. Let me just state it for SL2. So non-trivial, but it's true in general for SLN. The bounds get better, not worse, and for linear algebraic groups. It's nothing special to SL2. So I will say or other SLN, though there the bound is actually better. They are all big. They all have dimension at least q minus 1 over 2, where q is the size of k. So this means that lambda 1 has high multiplicity. No, but this means then that this sum here is, of course, at least the multiplicity of lambda 1 multiplied by lambda 1 squared. We just ignore all the other terms. So we obtain that lambda 1 is at most G over A, and this is actually quite small. When A is large, no? When A, as in our case, is bigger than G to the 1 minus O of delta. That's quite small. So you're going to have G to the O of delta, so Q to the O of delta here, basically. I'm going to have Q to the minus 1 over 2 plus O of delta. It's very small. But what does it mean when so lambda 1, and of course all these smaller eigenvalues are at most these. What does that mean? That means that a walk in the, well, for that matter, the application of the adjacency operator makes things close to uniform very, very quickly. Very quickly. So for any f, this converges to a uniform function very quickly. Extremely quickly. In fact, already in our case, what we really use is that already for 1 or 2 steps, you have something close enough to uniform that it doesn't vanish everywhere. It doesn't vanish anywhere. Or there's a very, this idea, see notes. Do you think I should finish this? Do you prefer 5 minutes of technicalities or 5 minutes of blah blah? So this idea, see notes, suffices to show that this thing, so if you apply the density operator to 1A and you take the inner product to 1GA, this is non-zero. So this is just a clever, efficient way to do it. If you do it in a silly way, you get a to the 5 rather than a to the third in the conclusion I'm going to write down. For every G, but this means that G is in fact in A cubed, or otherwise this scalar product would in fact vanish. So you get that A cubed is G of K when A is bigger than. Oh, and this is, as I said, Gowers-Nikolov-Piver. But if you get A to the 10, it's less elegant but just as good, and it's simpler. And you could do it less elegantly as well. All right, so that's about it. Let me just briefly recapitulate things. So I have given you here the proof of the main theorem. No? And by now, and I have given you a proof that generalizes in a fairly straightforward way. So this is true now. This has been proven by now for all groups of Lie type of SLN, SP2N, really exotic groups of Lie type and whatnot. There's only one sort of fly in the ointment there. It's the fact that here delta depends on n. Well, n is equal to 2 here, so delta doesn't depend on anything here. Here delta is really a constant. But when you prove it for SLN, delta does depend on n. And that's not just a feature of any weakness on our part, that's actually a feature of reality. If this statement would not be true for a arbitrary in SLN, delta has to depend on n. However, the consequence, so the proposition, as I said in the first class, has a very nice consequence. It has the consequence that, the immediate corollary, that the diameter of any Cayley graph of SL to K is bounded by a power of log G, where these constants are absolute. So this is Babai's conjecture for SL2. So this was the first case of Babai's conjecture to be proven. And now we have, because of this, Babai's conjecture for any group of bounded rank. Why do I say of bounded rank and not for every group? Well, we do get a bound for every group, but we get an exponent and a constant that depend on n. And that's believed to be unnecessary. So this is believed to hold without a dependence on n for all simple finite non-abelian groups. And now it's known now, with a dependence on n, so in SLN, SP2N, SON, etc., for G of Lie type. Now, what reasons are there to believe that this should be true without a dependence on n, this conclusion, given that the proposition the dependence on n is real? Well, Siemens, I said all simple finite non-abelian groups, and the conjecture here, the conjecture is older for Siemens, or, well, all 10 is really simple. Let's say Siemens. And everything indicates that it's true. This older conjecture is in fact true, and with Sheresh we have a bound for the diameter for Siemens, which is not as strong as this. So I remind you, maybe I mentioned it, that for G equals Cmin, and again A arbitrary, we have that the time runs out. We have that the time runs out at the precise moment I wanted it to run out. So this is 4 plus epsilon. So it is not quite as strong as that, but it's a big step in the direction, I would say. So it makes the conjecture that this is true for Cmin much, much more plausible. And I think the time is ripe for further improvements on this. This is a result from 5 years ago. So it's up to you to improve it. And why is that and that really plausible evidence towards our conjecture is because, and I will finish with a highly mystical statement, which people other than myself hold on very dearly, for me it's just a nice statement, is that Cmin should be seen as PGLN over the non-existent field with one element. I will just let you contemplate that bit of religion, and in this note, I finish the course.
Questions?
Yes.
So I want to make sure that I understood your comment about the product theorem, the like delta depending on n.
Yes.
Like for any like generating subset. So could
No,
it be,
I mean there are really nice generating subsets as well, but there are
Okay.
evil generating subsets for which delta has to decrease at least as rapidly as 1 over n.
okay, so it could be that there, or maybe there are like magical.
Well, they're
Like a
not
magical
most.
sequence.
Most A's are
Okay.
good. Yes.
Okay, that answers my question.
Okay.
All right, let's thank Harald again.
Let me put it. All right. Let me see.